Hello, my name is Benjamin Kincaid, and my talk today is on a new generation of effective core potentials from correlated and spin orbit calculations for selected heavy elements. So, effective core potentials are a valence-only replacement for all-electron calculations, freezing or removing inner shell electrons which do not play a vital role in the atomic gaps, and seek to remove the Coulomb singularity. There are two major classes of effective core potential that we will talk about today. Those are the average relativistic effective potential, or AREP, which reproduces scalar relativity, and the so-rep, or spin orbit relativistic effective core potential, which provides J splittings. All of our correlation consistent effective core potentials, or ccECPs, are constructed using atomic spectra and norm conservation as the objective functions for their optimizations, and are made to accurately reproduce the hydride and oxide binding curves for each element that we test. All of them are available in various useful formats, such as Gaussian UPF and MolPro, and so on. All of the elements labeled as black are already tabulated, and all of the ones in red are the ones that are currently being demonstrated in this particular work. Here we have the tungsten atomic spectrum discrepancies. So on the left, we have states that the atom is in. Here we have the all-electron data. So the all-electron data is calculated using the most accurate we can afford, which is coupled cluster with singles, doubles, and perturbative triples with a large uncontracted saturated basis set, in this case, a giant TZ basis set. And all of these values are in EV for the gaps. The MWB, Lanel, SPKJC, Krenbol, MDF-STU, these are all previously tabulated ECPs that are available to the field. And these are their discrepancies with respect to these gaps on the left in EV. Here we have our ccECP, which has, looking at the very bottom, the best mean absolute deviation out of the bunch. And this essentially says that we have the least error across the entire spectrum. We'll talk about LMAD a little bit later, and WMAD simply weights towards smaller gaps having more of an impact on the final number. Here's the tungsten molecular binding curve discrepancies. So the left is the tungsten hydride, on the right is the tungsten oxide, and these are the discrepancies with regard to the all-electron. These are, again, coupled cluster, singles, doubles, and perturbative triple numbers that we're comparing against. So the gray region is chemical accuracy, and our ccECP in green is in chemical accuracy for the entire range for the hydride. The vertical dashed line is the equilibrium bond length. And for the oxide, you can see that our ccECP well outperforms all the other competitors with regard to being within chemical accuracy and trying to recreate the binding energy over the entire spectrum on the whole. Here we have the atomic spectrum performance, essentially a review picture of how all of the ECP families fared on each of the elements that we investigated. So these are the mean absolute deviations for the spectra for each of the elements. So we have iodine, tellurium, and so forth. And you can see at the very bottom, our ccECP in green has the lowest mean absolute deviation across each of the elements that we investigated, performing quite admirably, and even reaching into the edge of chemical accuracy, which is the gray shaded region again, near zero on this curve. Here we take a chance to zoom in to the LMADs, which are the low-lying mean absolute deviations. So these specifically focus only on the electron affinity, first and second ionization potential gaps. And over all of the elements that we investigated, our ccECP is actually within chemical accuracy for these states, at least on average. And in some cases, we significantly outperform some of the previous available ECPs. Here we have the ccECP performance for various molecular parameters. For each element, we constructed a dimer out of these using these ECPs, each family, and then we did a Morse potential fit of the binding energy curve. And from that, we extracted the equilibrium bond length, the dissociation energy, the vibrational frequency, and the energy at the dissociation limit. And we compared these against the all-electron values. And so these are the mean absolute deviations for all of the elements for each family of ECP. So the closer to 0, the better. And as you can see, our ccECP outperforms pretty much all the others quite handily. Here we have the spin orbit multiplets in complete open shell configuration interaction in fixed phase spin orbit diffusion Monte Carlo for tungsten. So looking here, we have the all-electron gaps in EV for various states that we tested. These are J-splitting states. And here we have the Stuttgart numbers, the Stuttgart ECP, and their deviation from the all-electron. And here we have ccECP. And so we have the mean absolute deviation at the very bottom, and we outperform the Stuttgart quite handily in COSI. Here we actually have the fixed phase spin orbit diffusion Monte Carlo, which is a much more taxing routine. And in this case, we compare against experiment. And here we can see that the ccECP once again vastly outperforms the Stuttgart with regard to comparison to experimental numbers. Here we have the dimer binding energy curves for the spin orbit terms for the Stuttgart and ccECP. In green, we have the ccECP with the up triangles being our spin orbit and the down triangles being our just our AREP, so no spin orbit. Similarly, in purple, we have the spin orbit for Stuttgart being the circles, and it's hard to see, but you can see over here a little bit better. The squares are the AREP, so no spin orbit. Tungsten's kind of a unique case in that the experimental data is rather poor. This red shaded region is the error bar on the experimental number that we actually were able to find for the binding energy. There was no prediction from experiment as to what the equilibrium bond length should be. So the fact that the two ECPs agree actually provides a decent prediction as to what it should be if experiment were to be conducted to find the equilibrium bond length in the future. Here we have the iodine dimer, and you can see that our spin orbit ccECP actually fits very nicely with experiment, and including our predicted equilibrium geometry lays right next to the vertical red line indicating the experiment. And here with the binding energy curve, the binding energy at the equilibrium is very, very close to what we get with experiment as well. Moving on to bismuth. Bismuth, there is more of a deviation, but this is to be expected because bismuth is a main group element and not a transition metal. It means that its valence space is very restricted, so we have very few electrons to try and recover the binding energy properties and the bond length that we expect. So this is a problem with all ECPs that are trying to recreate sufficiently small valence spaces. So this is not unexpected, and we still see a significant improvement over the previous Stuttgart. And with gold, you can see that we lay right in the expected region for the experiment. Moving on to conclusions, we have new ccECPs for iodine, tungsten, and so forth, and they're accurate at both the AREP and spin orbit levels. They show very close agreement when compared with experimental data, and they're available in various formats such as Gaussian, UPF, and MolPro. For each element, we have them available with DZ to 5Z basis sets for in all the formats described above. For all current ccECPs and basis sets, they can be found at the pseudopotentiallibrary.org, and all this data can be found and discussed in much greater detail on archive with our current paper that is under review after being submitted to the JCP. Thank you for your time.